close-packed structures. Let us now understand closed-packed structure. In solids, the constituent particles are close-packed, leaving the minimum vacant space. It can be explained with these examples. The first example is close packing of spheres in one dimension. There is only one way of arranging spheres in one-dimensional closed-packed structure. That is to arrange them in a row and touching each other. In this arrangement, each sphere is in contact with two of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in one-dimensional close-packed arrangement, the coordination number is 2. Close packing in two dimensions. Two-dimensional close-packed structure can be generated by stacking the rows of close-packed spheres. This can be done in two different ways. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first row. The spheres of the first two rows are aligned horizontally as well as vertically. If we call the first row as A-type row, the second row, being exactly the same as the first one, is also of A-type. Similarly, we may place more rows to obtain AAA type of arrangement. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the two-dimensional coordination number is 4. Also, if the centers of these 4 immediate neighboring species are joined, a square is formed. Hence, this packing is called square close packing in two dimensions. The second row may be placed above the first one in a staggered manner, such that its spheres fit in the depressions of the first row. If the arrangement of spheres in the first row is called A-type and the one in the second row is different and may be called B-type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. Hence, this layer is also of A-type. The spheres of similarly placed fourth row will be aligned with those of the second row, that is B-type. Hence, this arrangement is of ABAB type. In this arrangement, there is less free space and this packing is more efficient than the square close packing. It can be easily understood by seeing the above two diagrams. Each sphere is in contact with 6 of its neighbors and the two-dimensional coordination number is 6. The center of these 6 spheres are at corners of a regular hexagon. Hence, this packing is called two-dimensional hexagonal close packing. Close packing in 3 dimensions. All real structures are 3-dimensional structures. They can be obtained by stacking 2-dimensional layers one above the other. One of them is 3-dimensional close packing from 2-dimensional square close packed layers. The second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically. Similarly, we may place more layers one above the other. If the arrangement of spheres in the first layer is called A-type, all the layers have the same arrangement. Thus, this lattice has AAA type pattern. The lattice thus generated is a simple cubic lattice and its unit cell is a primitive cubic unit cell. And other is 3-dimensional close packing from 2-dimensional hexagonal close packed layers, placing second layer over the first layer. Since the spheres of the two layers are aligned differently, let us call the second layer as B. It can be observed from that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to different arrangements. Wherever a sphere of the second layer is above the void of the first layer, or vice versa, a tetrahedral void is formed. These voids are called tetrahedral voids because a tetrahedron is formed when the center of these four spheres are joined. They have been marked as T. At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. One of them has the apex of triangle pointing upwards and the other downwards. These voids have been marked as O. Such voids are surrounded by 6 spheres and are called octahedral voids. The number of these two types of voids depend on the number of close packed spheres. Let the number of close packed spheres be n. Then the number of octahedral voids generated is equals to n, and the number of tetrahedral voids generated is equals to 2n. Now placing third layer over the second layer. The first one is covering tetrahedral voids. Tetrahedral voids of the second layer may be covered by the spheres of the third layer. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This pattern is often written as AB-AB pattern. This structure is called hexagonal close packed structure, that is HCP. We can see that 4 layers are stacked in each case. The second one is covering octahedral voids. ABC type of arrangement of layers when octahedral void is covered. Fragment of structure formed by this arrangement resulting in cubic closed packed or face centered cubic structure, that is FCC.